Hello again. So I will introduce myself, even though it's not my first talk, in case somebody is looking at the recording. My name is Luca. I work as a software engineer in the Linux systems group, where I work on the Azure infrastructure on Microsoft. By day, by night, I'm a systemd maintainer, Debian developer, a bunch of other stuff that I continuously neglect. So I'm here to talk to you about a new way to reboot. So, soft reboot, or how to atomically replace your root file system and reboot user space without the kernel being any wiser. So, status quo. You can reboot in a bunch of ways. So the kernel supports sysfs to specify warm reboot, or cold reboot, which means cutting the power, or something called CPIO reboot, which I have no idea what it is, but it is documented, and the sysfs supports it. Newer, but not that much, is still quite old, re-exec. So instead of going back to the firmware and the hardware, you load a new kernel initd in the kernel, and the kernel itself jump into it. This allows you to cut some time during your reboot process. So now we are doing soft reboot. This only restarts user space. The kernel doesn't notice anything. It's a new feature in systemd 254. Except there was already a soft reboot, and I noticed while putting together the slides last week. So if you look at for that kernel interface, it defines soft reboot as a synonym of the warm reboot. So we got a bit of a name clash there. Oops, a bit too late now to change it though. But why do we want to do this? And the answer is always performance. So for the Azure project I work on, performance is critical, especially at reboot. So on any headless system, a server, IoT, offload card, whatever else, if you're providing a service and you need to update the OS to fix bugs, this causes a service interruption. And people don't like that very much, especially customers and people running VMs in Azure don't like that very much. So we try to minimize this. First thing we did, we talk more about Azure Boost tomorrow afternoon if you're interested. But in general, the first thing you do is you go from standard kernel reboot to a re-exec. So again, as mentioned before, you cut some time. So when we were thinking about this problem, the obvious next step was, well, we cut the firmware time, now let's cut the kernel time and save even more time. And this is how soft reboot idea came to be. So the overarching goal is, minimize service disruption as much as possible, in any way possible, whatever the cost, as long as it doesn't require new hardware that costs money, because that is a no-no. I think this concept pairs quite well with the image-based Linux model that we spend so much time talking about, because the rootfs and the UKI that Lena talked about earlier this morning are distinct and discrete components of your vendor-provided OS. So they can be updated independently, and they most often are. For example, my Debian machine, I get a new kernel twice a month or so. I get more security updates more often than that, just as an example. So this also pairs nicely with live patching. So Red Hat, Ubuntu, SUSE, and more ship a kernel live patching feature that allows you to load a kernel module that will change the kernel live and update it. So this idea of updating user space separately from the kernel pairs very well with this, and we will use it like that in Azure. Now, again, the idea is the whole user space is replaced atomically and rebooted into. Now, for traditional package-based distributions, this might be less useful. It's more, the use case specifically for us is the image-based distributions. But even there, there are some components that, when updated, you cannot just restart them, like dbus. If you update dbus on your system, you cannot restart the dbus service. It will kill a bunch of stuff. So maybe soft reboot will be useful to cut the time of reboot when some of these components are updated. Just an idea. So let's look at how we do this. Again, as far as the kernel is concerned, everything is perfectly fine. Nothing is happening, nothing to see, move on. Which means a couple of things. For example, the boot ID, which is a UID that the kernel makes available under proxys or sysproc or whatever, doesn't change. So if things are based on that, then you soft reboot and there's no difference before and after. For example, UniCTL list boots doesn't know the difference, and we should probably fix that. And I'm sure there are more instances of this. So there are a few caveats to keep in mind. As far as user space is concerned, this is just a normal shutdown. We go to the normal process, the units are stopped, they're killed, blah, 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 etc. All is the same as it always be. System D is where the magic happens. So System D goes through the usual shutdown phases, but then instead of doing the reboot syscalls and giving control back to the kernel, it reloads and re-exec's itself. Now, how you do this, it's either in place, so you can reboot in place and not update anything if you just want to quickly reset user space. But more usefully, you want to reboot into a new rootfs. So the API is that you prepare the new root file system under /run/next root. And you can prepare anything you want under there. For example, if you have an encrypted disk, and that takes quite some time to get the key and unencrypt it and mount it and create a device mapper and whatnot, you don't have to redo this because it's already available. So you just mount it under next root in the appropriate location. Same thing for any disk or optional mounts. You can prepare it ahead of time. And again, this is a way to shorten the interruption time when the software boot happens, so you have fewer things to do where you can get away with it. Kernel configuration, again, the kernel is maintained as is, so nothing changes there. So yeah, you have a new software boot systemctl verb, and equivalent debus API. So Lennart added this in 254. I helped out a little, but he did most of the work, even though he not always liked what I did there, but I did help a little. For example, we have a new signal. So there's an existing prepare for shutdown signal the system sends when you reboot, but it doesn't tell you what kind of boot is happening. And for my use case, it's useful to know because, again, the kernel doesn't change. It's not restarted. Devices are kept exactly as is. So if you have any housekeeping you normally do at shutdown with devices or hardware or anything, it's good to know that this is a software boot and you can skip all of that. So there's a new prepare for shutdown with metadata that tells you, yeah, this is a software boot or a hardware boot or whatever else. It will be in the next version. So, I mean, this is pretty much the main part, right? It is remarkably simple in a way because it is very similar to the normal init-rd rootfs transition or the rootfs exit-rd transition. So it was surprisingly easy to implement. Now, there's a few more things that you can do on top of it, right? Not just shorten your reboot, but even improve things where you come back. So the previous speaker talked about the file Descriptor Store. This is an underdocumented thing, which is a fantastic feature, and I wish more software supported it. Our staff uses it. It's great. It allows you, again, as the previous speaker said, to give resources to systemd, sockets, MFDs, opens the connections, whatever, and then you get them back on when your service restarts. Now we extended this so that there is a new option there, store preserve, and if you set that, then the file descriptor store will survive the software boot because systemd is just restarting itself, so it passes state to itself on software boot. So your service can have open sockets, open connections, you give them to systemd and you get them back on after a software boot has finished, so you have even smaller interruption rather than a normal reboot because we can pass through all this state. Another thing you can do, for example, with interrupted, you can configure it so that it maintains the same configuration. Again, given the devices are not touched, the kernel is not touched, the network interface and network cards stay configured, they don't change. So with this flag, you can tell networkd, when you restart after software boot, please don't touch the interfaces, leave them configured. This means that all the open connections stay alive to the whole process because the interfaces are configured, the sockets are open, they're given to PID1, they're kept there and open. So the kernel keeps receiving stuff and buffers them until the software boot is finished and you get the socket back and you can start processing again. So /run is also passed through from the previous boot, is not reset. So if your service is storing state under runtime config directory or things like that, you will find it there as well when you are restarted after a software boot. It's another way to pass state through other than the file descriptor store. Note that this is not recursive, so only the top-level run mount is passed through. Tempfs, given its /tmp, is scratch error, it's supposed to go away, so we wipe that away and create a new tempfs there. Now, is that really it? Well, there's more. I talked about portable services before. I think it's an awesome feature. Again, in case someone is watching just this recording, a portable service is a way to create an image with a system unit inside, and attach it to a running system. This will run independently of the OS root file system. Now, this is, if it isn't independent of the root file system that we are updating, can we keep this running during the soft reboot? And the answer is, well, yes. So the network is accessible. The disks are accessible. If we manage to pull this off, then these portable services can experience zero interruption while you do a full reboot of your user space and replace the rootfs, which means you go from a little interruption to zero interruption. And zero interruption is great. It's exactly what I want. Now, there's some catches, though. They really need to be disconnected from the rootfs. If you have any references open to any file in the OS rootfs, then the mounts will be kept around by the kernel. You won't see them anymore, but the kernel will not release the memory, so you keep occupying that memory. So you really need to be sure that these portable services do not use resources from the rootfs if you want them to survive. And also, if your OS is going down, your OS services like network D or the dbus, they're going to be restarted. So there is a window of time during which they won't be available. And if you use those resources via IPC, via dbus, whatever, varlink, whatever else, you need to be able to handle the fact that you won't get an answer. You might, if they're not using the file descriptor store, you might even get a connection denied. And you need to be able to handle this in your portable service. Now, one of many reasons it's awesome is that the configuration is fully declarative. So we say in the unit, I am using this resource from the host OS via bind paths or bind read-only paths. It's all declaratively configured. So an idea I have, this is not implemented, but we could perhaps try and figure out from a surviving portable service, is it using anything in bind path or bind read-only path that points to the rootfs and then swap it automatically using the mount beneath API that there will be a talk for in the afternoon. This is just an idea. It's probably complicated and tricky to pull off, but I will look into it in the next few months. Now, how do we configure this then? This requires to set some specific options so that your service survives the 4 phases of soft reboot that happens inside systemd. This means you have, first of all, you have to say the 4 dependencies no. What does this mean? By default, any systemd service will be assigned implicitly some dependencies and ordering. For example, it will conflict and order itself before the shutdown target, which means it will stop us when you do a soft reboot, but you don't want that, so you define the 4 dependencies no, so you skip the transition. But that means you also won't be stopped during a normal reboot, which is not what you want. You want to keep your ordering and your conflicts there with the reboot, the hard reboot, the power off, and whatnot, so that your service is shut down gracefully and in the correct order during a normal shutdown. So you have to say the 4 dependencies no, and then manually say that you conflict with the reboot target and you order yourself before the reboot target. This will be added implicitly, but because of the first option, it doesn't happen anymore. Same thing for re-exec, same thing for power off, and same thing for hold. Now, I have no idea what the difference is between power off and hold, but you have to do that. This is the first transition, shutdown. We stop all the units. And to do this, your portable service will be configured to survive that one. There's also other ordering added by default. Now, usually portable services are not early boot services, which means they run after the basic target. That means essentially a bunch of basic stuff like var and basic system services like dbus are already set up after you run. This ordering after basic target ensures that, but you lose it because of the 4 dependencies no, so you have most likely to put it back. Next, the second transition. So there is the isolate operation the systemd does. If you're not familiar with it, isolating to a target means everything that target includes directly or transitively as a dependency is kept running, anything else is stopped. You don't want that because this happened on software boot, and when we come back, so your service will be stopped. So you have to say, please ignore me when you're doing an isolate. The third transition is sig term. After all services have been stopped, we've done the isolate, then we send a bunch of sig terms to remaining processes to clean up. You have to ignore that. Finally, there's the final phase, which is sig kill. To make sure that nothing is left, we also send a bunch of sig kills to any remaining processes at this point. Because again, this is the right thing to do. We want to make sure that nothing from the old OS survives the transition. But it means you have to configure yourself to avoid that. And to do that, you have to change your code in your executable and set the magic string for argv00. This is a pre-existing interface that is targeted at storage daemons in initrd, for example. And we reuse that for the same thing. Now, these are what you have to do. Now, I would like to have something a bit better than this. I like higher level interfaces. I would like to have a specific option for that, but there is a discussion ongoing on open pull request, and we'll see where we'll land. I would much like to provide a first-class, well-defined API where we can make a promise and say, yeah, configure me to survive software boot, and we'll do what we need to do. But there are different opinions, so we will see what happens there. At the moment, in systemd 254, you have to do all of this. And I have 4 minutes left, and that is all for my slides. So questions?
Is this on? Yeah. Hi, thanks for the talk. It was nice. Question, does this also work for operating systems that only use a user partition for AB booting and have a tempfs root?
Yeah, I think so. So I showed you in the second slide, the interface is that you prepare the new file system, new rootfs under run next root. And what you prepare there is intentionally left as an exercise for the reader. You prepare it however you want. If it's a tempfs, you mount a tempfs there, and you mount your user. We do not have anything to set these things up for you. It's maybe something we should look into, but at the moment, I mean, this is the first version on this stuff ships, so as always, it's iterative improvements, right? At the moment, you have to set up everything by yourself, and you can absolutely do that with the /user partitions, yes.
And one follow-up question, do we intend to like reuse code from what we do in initrd in here? Like, for example, not have /sys root, but just use run next root in initrd. We don't have that we can use the same concepts here as the initrd to stage 2 transition.
Yeah, I mean, again, the code that implements it is pretty much the same. We just had to add a few more things, but it was pretty much just initrd to host transition. So exactly the same thing will work. Yeah, absolutely.
Thank you.
How is the role that portable services fill different from that of containers running on a very minimal host operating system?
So the question was about difference between containers and portable services. So the main difference is that a portable service is run by systemd as if it was a system service. So a container is usually targeted at some compute case. You want to deploy something that does some calculation and you give it payloads or a DNS server or something like that. Portable services are much better for cases where you want to integrate in the host operating system. That's how I use them. So you have a bunch of management stuff, but it doesn't come from your OS partition. You want them manage them completely separately on different images and whatnot, and that's where you use portable services. In case of software boot, now I'm not super familiar with a lot of the container details, but if the container implementation requires a process from the host to remain running to manage your container, then you're going to have a problem. If you have something that just launches the container and then it just exits it, so there's nothing left back, then it should work. And you can just configure it like that if you manage it as a service systemd unit to survive. So that's a difference with regards to software boot. You have to check if there's a container manager like dockerd, then it probably won't work, unless dockerd can take the state of the running containers and transition it via the FD store, but it probably doesn't. There would be a way to implement that, but that's the main thing to look at, yeah.
Related question to this, do portable service processes also protect themselves with the @ sign?
So you have to do that, yes, if you want them to survive the final sig kill, yes.
Thanks.
More questions?
Over there.
So if I configure my service as you shown to have it survive, will just the binary or the process survive, or will also the service metadata in systemd be transferred?
Yes, so systemd transfers its state, so all the metadata is transferred to, so it will survive, yes.
Maybe this is not a problem at all, but my usual question, like, will it work with SC Linux? Because like the new packages can provide a new version. So we are like unloading the policy and loading a new one?
I use SC Linux in my product, so I updated the policy. I don't know if it made it up to the ref policy upstream, but our SC Linux people take care of that. But yes, I updated the SC Linux policy for this. Any other questions?
Yeah. So the interface for network D, which wants to not shut down the connection, if I understood correctly, the configuration now, it will also not shut down the connection when it's stopped as a normal service stop, right?
I don't know. I haven't looked into that.
Yeah, because that's right. So you had keep the HCP on stop. So it looks like this will need to be a separate case configured separately.
Okay, I haven't thought about that at all, so it's a thing we need to look into. Yes, thank you.
This is kind of the same thing, like if we consider a soft reboot just a plain shutdown and we have no way to distinguish, how can you like, oh, this service is misbehaving, I'm gonna restart it to like have it entirely like start from scratch, versus like, this is a service that has been written with the fact in mind that it survives soft reboots gracefully. I think we need to have a distinction to understand.
I agree. What a coincidence. Yes, but we need a way to mark that so that we know the service needs to do that. But at the moment, yes. So if it's the same thing as the existing root storage daemons, they all right now. This is a thing that's been supported for many years. You do that add thing, and then they will survive. And that's done because your root storage stuff, you want to survive it after a shutdown, so you can now mount cleanly. And yes, if they misbehave, then yeah, it's a problem. But yeah.
So you say that you need to configure network D to keep the DHCP address, right?
Yes.
But shouldn't network D really be listening for the soft reboot signal that you send out and then putting all that state in the FD store and just doing that automatically?
Yes, thank you for volunteering to implement that. I will be reviewing your PR happily. But yes, this ties back to what Zbigniew also said. Yes, we should do something like that. This is the way right now in 254 you have to do it. But yes, we should do better, yes.
More questions?
I think we are out, well, one last and then we're out of time.
Is there an interface to introspect how the current system was booted, if it was through a real boot or a soft reboot, and if so, where the root file system comes from?
Well, do we have it? I don't think so.
So we currently don't have that, but what I would like to add is like the generation counter or something that we maintain in PID1, and then it's 0 initially, and then as it goes up.
It goes back to the Jonas ETL thing, with boots. We need to integrate something like that so we can maintain account, but we don't have it yet.
So the reason why I didn't implement this yet is because there's some similar case that is also unrelated, which is some of the cloud vendors want to be able to clone VMs, and then they have VMs that basically have the same identity as the original one, but probably also should have a different identity in somewhere. So I have a suspicion that this generation counter, like they came up with the idea of a generation UUID basically that you have in addition to the machine UUID. And then so this makes me wonder if the generation counter should actually be the generation UUID and be the same thing that these cloud vendors want. But yeah, that's the only reason, because that's why we haven't implemented anything like that. But maybe we want both, I don't know.
Yeah. Anything else? I mean, we have 2 more minutes. I guess we're breaking for lunch anyway. There's no talk next. So if there's any more questions, we can take them. Otherwise, we can go have lunch. Going once? Going twice? Well, thank you very much for listening.